All right. Yeah, good morning, everyone, and welcome to lecture 6 of 124103. I'm sorry I was not able to be here on Wednesday. I was just really unwell that time, but I hope Patrick was able, yeah, I think he was able to cover the lecture slides that I prepared for that class. So just a couple of reminders before we start the first mastery test. It's actually the second mastery test, but it's the first one that's assessed. It's due tonight. 10 p.m. tonight. So make sure that you log on to stream and access the mastery tests before 10 p.m. tonight. It's the the topics covered in the mastery test is everything we've been talking so far up to free fall. So up to lecture 5 will be covered in the first mastery tests, and the level of the questions in the test are similar to the workshop questions and also the examples that we've been looking at in our lectures. So it's an open everything test. You can refer the to our lecture slides, to your notes, to the lecture videos. You can even search the internet like uh, Google. But you're not allowed to interact with other people within or outside the course. Other than that, you're free to look at references. Yeah, and then the other thing I wanted to remind you is the due date for the first lab. The first lab homework is due on the 20th, which is a Sunday. So you have this weekend would be your last chance to do the homework and submit that onto stream. So you only need to submit the last page of the worksheet of the worksheet, the lab worksheet. You can do the first part, the tasks in the first part, sort of as practice, but the page that I will mark will be the last page that you will submit onto stream. And if you have any questions about the mastery test or the lab, so feel free to pop it in the chat or ask me at any point during the class today, or send me an email. Um, yeah, I'll try to check my emails during the weekend. I realize the deadline is weekend, but I do check emails during the weekend as well. So if you get stuck or for some reason, just feel free to send me an email, and I'll try to look at that and reply. All right, cool. Okay. Yeah, I think there are no questions in the chat box, so maybe we can begin our lesson for today on forces. So what we've been learning so far is describing an object's motion. We've been talking about an object, it's moving, and we learned the terms like distance, displacement, speed, velocity, and acceleration. And we learned how to calculate these quantities and as well as interpret motion graphs. So we've been describing the object while it's moving or while it accelerates. But we haven't really learned about why it accelerates or why it moves in the first place. We just described its motion, but we haven't seen why it moved it in the first place. What causes the object to accelerate, and that's the topic for, I think, the next three to four lectures, and we call that branch of mechanics dynamics. Right. So maybe we have some intuition of why an object moves, right? If you think about it, if you see a ball on the ground, for example, and you want to make it move, you would either kick it or push it or pick it up and throw it. Then you're able to make the ball move. So in other words, we do something to the object in order for it to move. We exert force. In physics talk, we say we exert force on the object to make it move. So force is the push or pull that we exert on an object that causes it to move. Force is a vector quantity, and that's easy to imagine. Again, we said vector means that the direction is important. And if you think about force, if you push an object to the left, so of course the object will move to the left. If you pull on it to the right, the object will move to the right. So the direction for which you apply the force is important in determining the direction for which the object will move. And that's why force is a vector quantity. The unit for force is called the Newton. It's a derived unit. Again, derived unit means that it's a combination of the basic standard units. And the Newton is a combination of kilograms, meters, per second squared. And you can think of the Newton as meaning 1 Newton of force is what is needed, is the force needed to accelerate a 1 kilogram object by 1 meter per second squared. All right, so Newton is the unit for force. Before we can analyze force and how it can affect the object's motion, let's first look at different kinds of forces. So this table summarizes the different kinds of forces that we will encounter. It gives some symbols because we'll be drawing sort of force representations or force diagrams. It will be useful to use abbreviated symbols to represent the force. So these are the symbols. Second column gives you the symbols for the force. Some forces act at specific directions. For example, weight force is always downwards, and we'll go through that one by one. So the third column gives you a summary of the directions for the forces. Some forces need to be calculated. They're not usually straightforward. And so the fourth column gives you sort of an equation that will help you determine the magnitude or size of that force. Not all forces need to be calculated. I mean, not all forces have an equation associated to it, only some of them, and we'll look at those equations as well. All right. Okay, so first let's look at the weight force, which is also sometimes called gravitational force. It's called gravitational force because it's the force that the Earth's gravity, that gravity, it doesn't have to be the Earth, it could also be the moon. So weight force is the force that gravity exerts on any object that has mass. Okay. Right. So then looking at that definition, we can intuit this equation for the weight force. It's the force that's exerted by gravity and causes the object of any mass to accelerate. And last lecture, you learned about G, the gravitational acceleration that has a constant value of 9.8 meters per second squared. If you include the direction, that will be a negative 9.8 meters per second squared in the downward direction. So weight force is the force exerted by gravity on any mass m that causes that object to accelerate with an acceleration of 9.8 meters per second squared. So this G here is gravitational acceleration. So therefore, you learned last time, G is acceleration that's always downwards. So it's always negative 9.8 meters per second squared if you include the direction. Therefore, the weight force is always directed downwards as well. And it has a unit of newtons because it's a kind of force. So here there's a little bit of conventional thinking that we often make when we talk about force. We often give that in units of kilograms or kgs. When you ask someone how much do you weigh, they usually reply, oh, I weigh 50 kgs, or what's the weight of this bag of apples that I'm buying? Oh, it's like 1 kg. So there's a little bit of changing the mindset that needs to happen, if you'd like to think of that way. So weight, when we say weight, that should be measured in newtons. And it's not just in kgs. Mass is measured in kgs, but you combine that with meters per second squared, the gravitational acceleration, and weight should be measured in newtons instead of kgs. Okay, mass. Okay, mass is what is measured in kgs. It's the property of the material. It's how much matter is contained in a material. So that is independent of position, and it's a scalar quantity. So it's the one that we measure in kgs. So yeah, if you do a correct physics sentence, it should be, what is your mass, or what is the mass of this bag of apples, and you state the answer, my mass is 50 kgs, or the mass of this bag of apples is 1 kgs, instead of my weight is 50 kgs. The correct way of doing that sentence in physics would be, the mass, my mass is 50 kgs. Okay. Yeah, and the more mass an object has, the harder it is to move that, because then you will need to exert a bigger amount of force to move that mass. So say you have an elephant that is more massive than even a few cats or kittens, you will need to exert more force to move this bigger mass. Okay, then and you don't need as much force to move the kittens with less mass. Okay. So mass and weight are different. Weight is a kind of force. Mass is an inherent property of the material that tells you how much matter consists that material. Okay, so just a little bit of example here to again draw the difference between weight and mass. An astronaut's mass is 70 kgs. What is the astronaut's weight force? Okay, there's an emphasis there of weight being a kind of force on the Earth and on the Moon. The gravitational acceleration on Earth is this 9.8 meters per second squared, while on the Moon it's only 1.6 meters per second squared. Okay. So how would you find the weight? What is the weight of the astronaut on Earth, and it's his or her weight on the Moon? Okay, so we know weight is a kind of force, and that's equal to mass times the gravitational acceleration of wherever that object is located at. So on Earth, the gravitational acceleration is 9.8 meters per second squared. The mass is the same, 70 kgs, and you have a weight of 690 newtons. Right? On the surface of the Moon, the calculation will still be the same, but the gravitational acceleration is different. So G will be the only thing that's different. The mass would still be the same because it's still the same astronaut with the same amount of atoms and electrons, and same composition on the Moon as it is on Earth. But because the gravitational acceleration is different on the Moon, the weight of the astronaut is different on the Moon. Okay, so mass is the same wherever you are, but the weight force will change depending on the value of the gravitational acceleration. Okay, right? Cool. Any question about weight and mass? Yeah, I hope the difference between mass and weight is clear now. The next kind of force is called the support force. It's more commonly known as the support force, but it's also known as the normal force. And it's called normal force because of the direction of this force. So normal comes from the Latin word norma, which means perpendicular. So it tells us that the direction of the force, the direction of this support force is always perpendicular to the surface that supports this object. So this support force requires that an object has to be on the surface of something. So yeah, so if it's supported by a string, if the object is supported by a string, for example, you have this pen that's hanging by a thread or a string, although you might think that the pen is supported, the kind of force is not a support force in this case of a string, of a pen hanging by a string. You only have a support force if you have a surface and you have the object that's being supported by the surface. It can be, as the surface, my background's messing up whatever I'm showing you. So the surface could also be vertical, and you might have an object that's leaning against the surface. This vertical surface would still be supporting this object that's leaning on the surface. So there has to be a surface that is in contact with the object that it's supporting for you to have a support force. Okay, so here in the figure here, you have a block that is supported by the surface of the table. And in this case, the normal force is directly upwards because it's perpendicular, okay, so the surface is horizontal. So the normal force should be directly upwards, and it's perpendicular to the surface that's supporting it. Okay, an inclined surface, just like shown in this left figure here. This inclined surface is supporting this box. The normal force or the support force should always be perpendicular to the supporting surface. So the normal force would be angled at 90 degrees. It would be this diagonal force here, and it should be angled at 90 degrees compared to this inclined supporting surface, right? Okay, so that's why it's called normal force, because the support force should always be perpendicular to the surface that's supporting it. Okay, right. Next force is called frictional force. It's the force that resists the motion of the object that is in contact with a rough surface. Okay, so this figure here illustrates, okay, right, the two objects have to be in contact, and there's supposed to be some sort of roughness between the two surfaces, and it's this roughness that resists the motion of an object on that surface. And the frictional force, it should be in opposite direction to the motion of the object. So we can see here, if the object is moving to the left, for example, the lawnmower is moving to the left, and there's the wheel is in contact to a rough surface. The surface provides this frictional force that is to the right, opposite the motion of the object. There are two kinds of frictional forces: static friction and kinetic friction. They're essentially, they just distinguish the kind of friction depending on whether the object is at rest. So static means the object is not yet moving, and it's this static frictional force that causes the object to remain at rest. So when you have an object on the surface and you try to push that object, sometimes you'd feel some sort of resistance. Okay? Sometimes you'd feel some sort of resistance, and you have to exert a little bit more force to get that object moving, and that's because there's this static friction that opposes the initial force that you're exerting to cause that object to move. And then once the object has started to move, you have this kinetic friction. Kinetic means at motion. So kinetic friction is the friction that's experienced by an object that's already moving, and you still have this force that's opposing its movement because of the roughness of the surface. So static friction, that's when the object's not yet moving. It's just in the process of moving. And kinetic friction is once the object has started to move, the static friction becomes kinetic friction. Okay. There's some equation involved with frictional force. So frictional force F is equal to some coefficient, mu. This is the Greek symbol that you read as mu. Mu, it looks like a fancy U, but we read it as mu. Mu is called the coefficient of static friction. It's a property of the rough surface. So it depends on how rough the surface is. A very rough surface would have a higher coefficient of static friction. And a smooth surface will have close to zero or negligible coefficient of static friction. Yeah, and it also depends on the normal force. Yeah, again, you'll have frictional force if the object is in contact with the surface. And so we learned earlier, if you have an object that's in contact with the surface, you also have this support force or normal force. And that's why it comes into the frictional force equation. All right. Does that make sense? Any question about the frictional force, or is anything unclear about the frictional force before we move on? Or, all right. Okay, so at this point, we're just defining the different kinds of forces. We haven't, we'll look at these kinds of forces in relation to the object later on. Right? Okay, so no question about the definition of the frictional force. Let's move on to the tension or tension force. Tension force is the kind of force that exists when you have a string, rope, cable, chain, or other non-elastic thing that's supporting your object. So that's the kind of force now that exists when a pen is hanging by a thread or a string. All right, the key here is the string, thread, cable, or chain should be non-elastic, meaning it does not easily stretch. Okay, once it easily stretches like a rubber band or a spring, there's another kind of force that's involved there. We'll talk about that in the next slide. But for non-elastic things like strings, ropes, and cables, it's the tension force that's involved here. The tension force is always directed away from the object. Okay, so in this figure here, the object is the light bulb. So the light bulb is hanging hanging on this cable that's connected to the ceiling. Okay, so although the ceiling technically supports the bulb here, the bulb is directly connected to the cable. So the bulb is directly supported by this cable. And so the kind of force that's directly associated and connected to this object, the light bulb, is tension force. And tension force is always directed away from the object, sort of like pulling on the object. And so in this particular case, the tension force is directed upwards along the cable, okay, and away from the light bulb, which is the object. All right. Okay, tension force. And the next force is what I was talking about when you have something elastic that is supporting the object, like a spring or a rubber band. that can easily stretch, then you have this elastic force. So essentially, say you have this spring that's compressed initially. If you hang a ball or anything that has mass at the end of that spring, we know that the weight force will pull that object downwards, because gravity will always pull on things downwards. So once you hang this ball that has some mass m at the end of the spring, the weight force due to gravity will pull on the spring downwards. So you have this downward gravitational pull on the spring, and that causes the spring to stretch. So you have here the stretch on the spring. Now the spring will want to go back to its original unstretched position, and it's the elastic force. Okay? The elastic force will try to bring back the spring to its original unstretched position. Okay? Right. And so the elastic force will now, if you think about it intuitively, the elastic force will try to bring back the spring to its original unstretched position. Let's say the amount of stretch that the spring had was delta x. Okay? Delta x being the extension of the spring. That's how much stretch the spring had. The elastic force will now be equal to how much stretch the spring had, delta x, times some constant value called the spring constant. So the spring constant is a property of the spring. The easier the spring is stretched, the smaller the spring constant. Okay. The bigger the spring constant, the harder it is to stretch the spring. Okay. And the negative sign here, the negative sign in the equation means that the elastic force is in the opposite direction as the stretch. But we'll talk more about elastic forces in lecture 9. We'll talk about compression and stretching. So we will look at elastic force in more detail in lecture 9. But I just introduced the definition of elastic or restoring force in this case to differentiate it from tension force that we've seen earlier when the supporting object is non-elastic. All right. Okay, so those are the kinds of forces in the table that we've just defined. So any question at all about those kinds of forces before we move on? All right. No question. Yeah, I don't see any question in the chat box. Okay, so why did we identify these different kinds of forces, and why did we define these kinds of forces that could exert, that could be experienced by an object? Well, because we will use these forces to draw what we call a free body diagram. So free body diagram, these are diagrams that show the relative magnitudes and magnitude or size and direction of all the forces acting on the object. Going back to our example of the ball on the ground, and you wanted to make that ball move, say you kick that ball, you're exerting this kick is the force that you exert on the ball. But there are also other forces at play. Maybe the ball is on the grass, so there's a rough surface between the ball and the grass, so there's frictional force between the ball and the grass as well. So there are other forces, and the ball has some mass, so gravity is pulling on the ball downwards, so you have weight force or gravitational force on the ball as well. So there are a lot of forces. There are other forces, multiple forces acting on an object simultaneously. And to visualize these different forces, we draw what we call this free body diagram. And we represent the forces using arrows. Okay. And to indicate that the force is a vector quantity, the arrow, the direction of the arrow will indicate the direction of the force, and the size or the length of the arrow will indicate the size of the force. And then, of course, we need to label the type of force that we draw on our free body diagram to identify what force is acting, because there are multiple forces acting on an object. So I guess right. So just some tips on drawing a free body diagram. Okay, when you draw a free body diagram, ask yourself, is there gravity? Because maybe the object is in outer space where there's vacuum and there's no gravitational pull, in which case there's no weight force, there's no gravitational force. So ask yourself, is there gravity? If there is, then there has to be weight force or gravitational force acting on the object. Is the object in contact with the surface? Is a surface supporting the object, in which case there should be a normal or support force? Is there friction? Is the surface rough? Okay. In that case, there should be a frictional force. Is the object tied to a string, a rope, or a cable? If it is, then there should be a tension force that's always directed away from the object. Yeah, elastic force will not look at that in this lecture at the moment. So we'll just bench that for the meantime. But if the object's connected to a spring or something elastic, then you have the elastic force, of course. And then is there an applied force? Like, did you kick the ball? Your kick is an applied force. Are you pulling on something? Your pull is an applied force. Are you pushing on something? The push is an applied force, in which case you have to include that in your free body diagram and label that as applied force, F applied. All right. So the easiest way to look to understand the free body diagram is to look at an example. Right. So say you have here a car that's being towed by a youth using a rope. Okay. When we say rope, we always assume that it's at least inelastic. I mean, it stretches a little bit, but it's not as elastic as a spring. So it's being towed by a rope along a level ground. So for simplicity, we'll assume that the drawing is not so much, but we'll assume that it's a horizontal rope that's towing the car. Consider frictional forces. The road is rough. So there's frictional force between the car's tires and the ground, but neglect air resistance so that air does not exert some frictional force. And we want to draw a free body diagram that shows the forces acting on the car. Okay, so can you give me one force that might be acting on the car? Can anyone, you can just type it in the chat box. Okay, yep, so tension force. So there's a tension force. Let me just. Yeah, tension force, it's because the car is being pulled by a rope. Yeah. And tension force, this is our object, is the car. Tension force is always directed away from the object. So when you draw your tension force, it should be directed away from the object. Okay, tension force. Okay. Yeah, weight force, because the car has mass. Anything that has mass will have a weight force. Yep, yeah. And what's the direction of the weight force on the car? Downwards. Yes, weight force is always downwards. Okay. Weight force is always downwards because gravity is always acting downwards. Yep. Yeah. Okay. Right. It's good you corrected yourself, Nikita. So the one that's exerted on the ground is frictional force. Okay. What's the direction of the frictional force? Is it to the left, to the right, upwards, downwards? Yeah. Frictional force always opposes the direction of motion. So the car is being towed to the right. Okay, the car is moving to the right, so you should have a frictional force that's directed to the left. Okay, anything else? Support force, very good, Kwangwin. Okay, so support force, because there's the road that's supporting the car. What's the direction of the support force? Yeah, upward. So support force should always be perpendicular to the supporting surface. Okay, I saw here applied force. Yes, the youth is applying that applied force, pulling the car to the right, but the youth is exerting that applied force via the rope. Okay, so so to label, so the applied force is embodied in this tension force that we put on the rope here, so we don't have to put the extra applied force in there, right? So yeah, so the correct free body diagram, you have 4 forces: normal force, that's upwards, weight force, okay, tension force, and frictional force. Okay. So for the relative sizes of the arrows, we'll look into that in more detail. Okay. So drawing this free body diagram and visualizing the forces. Okay, so what now? So now we have the free body diagram. What's next? Okay, why do we want to visualize these forces, and why do we want to draw this free body diagram to visualize the forces? Okay, eventually we draw the free body diagram and visualize these forces because we want to determine the net force that is acting on the object, net or total force that is acting on the object. So net force, it's the combination of all the forces on the object. And we want to find the net force or the total force because the net force determines the object's acceleration. Okay, so think, for example, there's a box on the surface and your friend is pulling on the back box to the left, but you're pulling harder to the right. Okay, so intuitively, you would think that the box will move to the right, right? Because you have, although both of you are pulling on the box, you are pulling harder to the right, and therefore the box will move to the right in the direction of where you are pulling harder on the box, right? So in this situation here, as we can see in the figure, say your friend is pulling on the box to the left with a force of 5 newtons, but you're pulling to the right with a bigger force, you're pulling harder with a force of, say, 10 newtons, then intuitively you know that the box will move towards you because you're pulling harder. So if you look at the net force on this box, you have 5 Newton pull to the left and 10 Newton pull to the right. The net force will be 5 newtons to the right. Does that make sense? Why it's 5 newtons to the right? Yeah. Yeah. Okay. So just even if you're just thinking of this intuitively, okay, you would know that yeah, the rightward pull is bigger than the leftward pull. So the net or the total pull should be to the right. Okay. And the amount of force, amount of pull to the right would be the difference between these two opposing pulls. right? So going back to example 1, and if we wanted to draw the correct size of the arrows, okay, so the rightward tension, should be bigger than the leftward friction. Yeah, it should be bigger than the leftward friction. Because then in that case, if the rightward tension force is bigger than the leftward friction force, that will cause the car to move to the right, to the direction of the bigger force. Okay? And if we apply that again, if we do the same intuition for the net normal force and the weight force, we can sort of intuit that, hey, okay, there's no motion along the vertical, the car is just moving along the horizontal, the car is not moving up and down. So that means that the amount of upward force provided by the normal force should be equal to the amount of downward force provided by the gravitational force. So these two should be of equal lengths. Equal length, meaning equal size or equal magnitude in the normal force and the weight force, so that the net or total force along the vertical will be 0 and the car does not move along the vertical. But along the horizontal, the net force should be towards the right. The pull towards the right should be bigger compared to the pull towards the left. All right. Okay, does that make sense? I hope that makes sense. Right, good. Okay, so force is a vector, so the length gives you the size of the force, the direction is the direction of the force. So conventionally, we'll take up and right as positive directions and downwards and left as negative directions. Okay, so try this little exercise. Find the net force in this scenario here. You have two scenarios shown here with corresponding forces. So what's the net force in the first case and what's the net force in the second case? Right, so what's the net force in the first case? You have two 5-Newton forces that are pulling on the block to the right. Yep, good. So both forces are moving to the right. Both are positive forces. Okay, so the net or total force should be to the right, and it's just they're both positive, so you need to add both forces equaling to 10 newtons. For the second case, you have two opposing forces, and they're both of equal size. So that means, right, these two forces would cancel each other out. Okay? You're pulling to the right with 5 newtons and your friend is pulling to the left with the same amount of force. So that means the block would not move. Right? The net force will be 0 in the second case. Cool. All right, so we've been looking at net force. We've seen the net force or the total force will influence the motion of the object. Okay, and we have actually 3 laws that describe the connection between the forces that act on the object and the resulting movement, or no movement in some cases, of that object. And these laws are called Newton's laws of motion. We'll look at the first law today. We'll look at the next two laws in the next 2 lectures. Okay, so the first law of motion says that, right, an object at rest will stay at rest. Okay, an object that's not moving will remain motionless, and an object in motion stays in motion with the same speed and in the same direction if there is no net external force acting on it. Okay, and that's why we draw the free body diagram to visualize the forces and then eventually determine the net force on that object, because the net force will determine the object's motion. If the net force is zero, okay, no net external force means the net force is zero, then that means that that object will keep doing what it's doing. If that object is at rest, that object will stay at rest. If that object is moving, that object will keep moving in the same direction with the same speed if there is no net external force. No net external force means that the net force along the horizontal should be zero and the net force along the vertical should be zero. Okay, we've seen in the first example, you can have forces along the horizontal, the friction and the tension, and you can have forces along the vertical, the normal force and the weight force. Okay, the net forces along the vertical and horizontal should be zero. Okay, and yeah, so here's a good example of Newton's first law in motion. Okay, so the reason, have you ever thought about why we are required to wear a seat belt when we are in a car? Okay. So imagine a car that's moving at 100 kilometers per hour and you're not wearing a seat belt. When the car crashes and comes to a complete stop, what will happen to a person who's not wearing a seat belt? Right? Okay, you're initially moving at 100 kph. Okay, the car comes to a complete stop, but you're not wearing a seat belt, an external, there's no external force that's stopping you. Newton's first law of motion says that you'll keep moving in the same direction and the same speed that you're going, and you become this projectile. Maybe this video would probably illustrate that in more detail. Okay, so have a look at this video. Can you hear, yeah, before we go on, can you hear the sound? Yeah, okay, good.
In a crash, the car stops, but everything inside keeps moving. It's the same inside your body. Even with the best protection, you're still vulnerable.
Yeah. Okay, that's actually an ad, so that people would wear their seatbelt. But you can see there, that if there's no seatbelt that will stop you from moving forward, you'll keep moving in the same direction with the same speed. Because according to Newton's first law of motion, right, once you've set an object in motion, that object will keep moving with the same speed in the same direction if there is no external force that will stop that object from moving. Okay. Right, so the only reason why we see things on Earth, the only reason why we see moving things stop is maybe because of friction between the object and the ground that causes that object to slow down and eventually stop, right? Even moving through the air, there's frictional force provided by the air molecules that will eventually stop that object's motion. But assuming that you go in outer space with, you're in vacuum, no air particles, no friction, whatever, okay, Once you start moving, you'll move forever, deeper and deeper into space. Okay, right. So it's the net force. It's the net force, the combined effect of the forces that influences the motion of an object. Right? Okay, that's Newton's first law of motion. Okay, and so looking at this example and applying Newton's first law of motion, okay, on this example here, say you have a mass of 2 kilograms that's resting on a rough. Okay, so some keywords there. If you read the word rough, that means there's some friction there. Rough level table. It's connected to a light string that's passing over a frictionless pulley. So this one has no frictionless pulley to a suspended mass, 3 kilogram mass, as shown in this figure. And we want to draw the free body diagrams. Right. Okay, we've seen earlier how to draw the free body diagram of a single object, the car. Now, what if you have two objects here, a 2 kilogram mass and a 3 kilogram mass? The approach here is to draw individual free body diagrams for each of the objects. So you should have a free body diagram for this 2 kilogram object and a free body diagram for the 3 kilogram object. Right. So yeah. So let's do the same exercise. Okay. Give me a force that's exerted on the 2 kilogram object. Yeah, any object that has mass, 2 kilograms, will experience a weight force, and weight force is always directed downwards. Okay. And the object is supported by the table, the desk. So you should have a normal force that's directed upwards. Okay. It says it's on a rough table, so you should have a frictional force. Why is the frictional force directed to the left? Okay, because the tendency of this object would be to move to the right. Okay, even if at the moment the object is at rest, okay, it will have a static frictional force that should be directed to the left, because if the object were to move, the tendency of this object would be to move to the right. And therefore, yeah, because of the tension force. Yeah. Thanks, Liza. Because of the tension force, the tendency of this object would be to move to the right if, if this 3 kilogram object were to pull it, it will pull it to the right. And that's why the frictional force should be to the left, opposing the impending motion of the object. Okay, in terms, so that's a cleaner free body diagram there. Right. Notice how the lengths of the arrows should all be of equal length, okay, because your object is at rest. So therefore, the net force along the horizontal should be equal to 0. The tension force should cancel the frictional force. So if the tension force is 10 newtons, the frictional force should also be 10 newtons in the opposite direction. Right, the net force along the vertical should also be 0, because your object's not moving along the vertical, it's not moving up or down. So the length of the weight force should also be equal to the length of the normal force. Okay. Right, if you draw the free body diagram for this hanging object here, okay, it has mass. Anything that has mass will have weight force. And it's supported by a string, so it should have tensional force. Okay. Tension, notice how the tension is moving away from the object, the 3 kilogram mass, and it's along the string. Okay. Right. Is there a normal force or support force for this 3 kilogram mass? Should we draw a normal force for the 3 kilogram mass? No. very good. Because normal force is only when you have a surface that's physically supporting this object. In this case, the string is supporting it. So it's the tension force that's supporting the object via the string. Again, the object is not moving, it's motionless. So the net force, there are only two net forces here. They're along the vertical. The net force should be 0 so that the objects will remain at rest. So the lengths of these two forces along the vertical should be the same. Cool. All right. Okay, so a note there, notice when I was discussing like net forces here, I talked about the net force along the vertical, normal and weight force, and the net force along the horizontal, friction and tension forces. So that means that when you determine the net force, you have to determine the net force along the horizontal independently from the net force along the vertical. Okay, you are not allowed to mix horizontal and vertical forces because the horizontal forces act along the horizontal axis, making the object move along the horizontal. The vertical forces act along the vertical axis, making the object move along the vertical. Okay, so so do not mix the net forces along the horizontal and vertical. So in this particular case of the 2 kilogram mass that has vertical and horizontal forces, you have to get the net force along the horizontal independently from the net force along the vertical. So if you look at the horizontal forces, just look at the horizontal forces. There are two forces along the horizontal, a tension force that's directed to the right. So that will be a positive tension force. Okay. Right. So if it's positive, yeah, it's positive, but we don't usually write the plus sign there. If we don't write the plus sign, it's assumed that it's positive. Positive tension to the right, and you have a negative frictional force to the left. Right, so there are only these two forces along the horizontal, and then when you do the net force along the vertical, just look at the vertical axis and consider the forces along the vertical. We said that upwards is positive, so you have this positive normal force, and you have a negative weight force. So this negative weight force, because it's directed downwards, negative frictional force to the left. Okay, and we don't combine these two net forces, right? Okay, is that clear about getting the net forces independently along the horizontal and vertical? Okay, good. Right. So along the vertical and horizontal, it's easy to get the net forces, right? It's just adding if they're in the same direction or subtracting if they're in opposite directions. But what if the forces are diagonal, like in this case here? You have one force that's at an angle of theta 1 with respect to the horizontal, and F2 is also diagonal with an angle. How do we get the net force in this case? One technique is called the parallelogram method, where you draw. So these are the two forces, F1 and F2, where you redraw the forces head to tail. So if you have this F1 force here, you draw the F2 force, okay, just copy this force, copy the second force and connect it with the first force in this manner. And then you also copy F1 and draw it connecting with F2. Okay, maintaining the direction of the forces. And then the net force will be the distance from where the forces tails are connected to where the forces heads are connected. Right, so notice how the tail of force 2 is connected to the head of force 1. And the net force connects the tails of the forces to the heads of the forces. Okay, so this is one way of finding the net or resultant force. In the next lecture, we'll talk at another way of finding the net or resultant force. So yeah, so let's look at this example to as an example of using this parallelogram rule to find the net force of two diagonal forces. So you have here a photo frame, a picture frame. It's weighing 8 newtons. So we're now given the weight instead of the mass. The weight force is 8 newtons. Weight force is given. It's hanging motionless. Motionless meaning it's at rest. That means net force should be 0 because it's supported by 2 wires. It's hanging motionless because it's supported by 2 wires with tensions T1 and T2. Draw a free body diagram to find the net force on the picture. Right, so we are sort of already given the forces acting. You have a weight force that's downwards, and you have these 2 tension forces. Okay, but to draw the correct magnitudes of the forces, okay, we know the weight force is downwards, it's 8 newtons. Right, for it to remain motionless, there should be an opposing force in the opposite direction that will oppose this weight force, and that will be the net tension force. So what would be, how many newtons should be the opposing force that will oppose this weight force to keep the photo motionless? Correct, right? It should be 8 newtons. You need an opposing 8 Newton force in the opposite direction of the weight force to keep the object motionless. Where will this 8 Newton opposing force come from? It will come from the 2 tension forces. So the net tension force, this is the net or total tension force, should be equal to 8 newtons in order to oppose this weight force. Right, so we know the tension force is along the string and directed away from the object, right? So this is a rough sketch, okay, for the tension forces. We know the tension force 2 should be directed that way and tension force 1 should be directed along the string. But to find the correct magnitude or length of the tension forces, we use the parallelogram rule. Okay, so the tension 2 and tension 1 should have these lengths, so that if you do the parallelogram rule, draw the tension 1, draw tension 1, the tail of tension 1 meets the head of tension 2. Okay, the tail of tension 2 meets the head of tension 1. Right, so you have this tension 2 here. Then you sort of form this parallelogram, and the net tension force connects the tails of the 2 tension forces and the heads of the 2 tension forces. You have this purple or magenta arrow representing the net tension force. That should oppose the weight force. Okay, so by drawing the parallelogram rule, you can sort of determine the correct magnitude or size of the 2 tension forces and draw the free body diagram to scale. All right. Okay, does that make sense? it will probably take a little bit of time to sort of absorb how you draw the parallelogram rule. But one thing to remember that could probably help you is when you're drawing the parallelogram rule, you draw what it's called, the head to tail technique, because you draw the second vector, the tail of the second vector, the tail of the second force should come from the head of the first force. So notice how, if you have an arrow, this is the head and this is the tail of the arrow. You notice how if this is the first force, change colors. Okay, so if that's the first force and this is the second force, okay, notice how, the first force, of course, will have a tail and a head. Okay, the second force will also have a head and a tail. Right, so notice how the tail of the second force is drawn from the head of the first force. And if you draw the second force again, if you copy in the parallelogram method, you're just copying forces to form a parallelogram. So you copy the second force onto the first force. Yeah, it's now tail to tail because you should not change the orientation of the force when you're copying it. You're just copying it, so you should not be changing the direction of the force. In the same way, if you copy the red force here, you're just copying the red force. Okay, so you should not change the direction of the force. You're just copying it exactly as its direction and its length. Okay, so at some point it would meet the head of the second force, and you draw the net force from where the two tails meet to where the two heads meet, and this is the net force via the parallelogram method. Okay. All right. I hope that made it clearer. Okay. So only when you're drawing two forces, like when you're drawing F1 and F2 initially, that's when you use the head to tail method. And then when you form the parallelogram, you're just copying the forces and you don't care about head to tail method anymore. You're just copying the forces as they are with their same directions and same lengths. And then find the net force. Right. Okay, and we'll have a lot of practice for drawing these forces and finding the net force in the workshop. Yeah, so if angle 1 isn't equal to angle 2, the net force line won't be vertical. How to adjust it to the graph? Yeah, you're right. So here, actually, the angle 1 is actually not equal to angle 2. You're exactly correct. And how to draw it so that the net force, it's exactly the reason why the net force is exactly along the vertical, because angle 1 is not equal to angle 2. Tension 1 will also not be equal to tension 2. And it's because tension 1 is not equal to tension 2 that the net tension is exactly along the vertical. Right? So you adjust it to the graph. It's actually this weight force that determines where this net tension force should be directed. That's why we drew the weight force first, because then we know that the net tension force should counteract this weight force. And from there, we can draw the correct tension forces adjusted to the angles of the strings. If the strings have the exact same angle, say right, if say they're exactly at 45 degrees relative to the horizontal, okay, then you know that the tension 1 and tension 2 should have exact same length, so that when you draw the parallelogram rule, so that when you draw the parallelogram rule, you will see that the net tension force will exactly be vertical, even if the lengths of tension 1 and tension 2 are exactly the same. And that would still counteract, the weight force that's directly downwards. Right. Does that answer your question, Oksana? Does that make sense? Yeah. So yeah, short answer to your question. Yeah, if the angles are not equal, you adjust the length of these tensions, tension 1 and tension 2, so that the net or total tension should be exactly vertical. Yeah, right, good. Okay. Right. Yeah, but that actually finishes our lecture, and I spent quite a lot of time doing this parallelogram rule and the net forces, because you'll actually need that for the workshop. So you can go through, you can proceed now to workshop 6. Okay. Yeah, it's on stream. You can download it from stream, and we're looking at different objects, drawing their free body diagrams. Yeah, and because we learned about relative magnitudes or lengths of the force arrows, and then we can draw the correct, hopefully we can draw the correct lengths of the arrows in these different cases here. Right. So the workshop is just all about drawing free body diagrams to indicate the different forces acting on the object. So we'll do the same thing. I'll give you some time. So maybe it's 11:15. So maybe I'll give you about maybe 20 minutes. At 11:35, yeah, maybe 25 minutes will be enough time for me to discuss the solutions. At 11:25, we'll look at the answers, but first I'd like you to try drawing the free body diagrams yourselves. I'll just stop the recording now.